I'd like to tell you orthogonal matrix means it is a square matrix. A square matrix in such a way that A is orthogonal if and only if A into A transpose equals to A transpose into A equals to I. A into A transpose equals to A transpose into A equals to I. That is same as saying that A into A transpose ij the entry of this is equals to ij the entry of this product. This is true for every ij, right? That means, this is a product of two matrices. One is A, one is A transpose. Therefore, ijth entry of the product. What is the ijth entry of the product? Summation k equals to 1 to n. Kth entry of this and kjth entry of A transpose equals to, this one. What is this actually? I is nothing but what? Identity matrix. It is looking like this. For 3x3 matrix. This is nothing but what? This can be rewritten as, what you observe is this is A11 entry, this is like A22 entry, this is like A33 entry. That means whenever two suffixes are same, that is 1. Whenever two suffixes are different, suppose you take A12, two suffixes are different, A12 is 0, this is A13 is 0. So what is this? This can be rewritten as Kronecker delta, delta ij. So ijth entry of the identity matrix can be written as Kronecker delta. What is Kronecker delta? This is nothing but whenever I equals to j, that is 1, otherwise this is 0. Is it clear? Is this clear, this step? ijth entry of the identity matrix can be rewritten as ijth entry of the, Kronecker delta, delta ij. ijth, so that means whenever I equals to j, that means it is equals to 1, otherwise it is 0. That means, this can be rewritten as, what is this actually? This, that I equals to 1 to n, ikth entry of this into, what is this actually? This can be rewritten as kjth entry of the transpose can be written as, jkth entry of the matrix. Kjth entry of A transpose is equals to jkth entry of A. And what is the Kronecker delta? Kronecker delta, this is 1 if I equals to j or j equals to I, otherwise 0. Right? That means, what does it mean by this? What does it mean by this? Whenever j equals to I, what does it mean by j equals to I? This can be rewritten as summation k equals to 1 to n. Whenever j equals to I, j equals to I means what? J equals to means what? Ik. This is 1, right? And, this k equals to 1 to n, summation k equals to 1 to n, ikth entry of A into jkth entry of this is 0 if j not equals to I. So what do I mean by this? Is it clear? Whenever j equals to I, what do you get it? J equals to I means what? Summation k equals to 1 to n, kth entry of A, here j is replaced by I, right? So that is exactly precisely summation k equals to 1 to n, k equals to 1 to n. This is nothing but, this is whole square equals to 1, and this is true for every I, and summation k equals to 1 to n, ikth entry of this and jth entry of the matrix is 0 for every j not equals to I. That means, what can you conclude? This stands for, already told you, this is nothing but sum of the squares of the elements of the any row is equals to 1. What do I mean by this? Sum of squares of elements of each row or column. Suppose you take I equals to j, here j equals to I substitute. Understand? Here I can I is replaced by, j is replaced by I. Once you substitute, in a place of I you substitute j, you can get column. So that means what? This is true for column also. So sum of the squares of the elements of each row or column is equals to 1, is equals to 1. And what I mean by this? Sum of the products of, what I mean this? Sum of products of elements. Sum of the products of, what I mean by this? What does I mean by this one? What does I mean by this one? Sum of the products of elements of any row or column, right? With the corresponding elements of any other row. Corresponding elements of any other row or column. Means J not equals to I, na? Other row or column is 0. So this is what actually definition of orthogonal matrix precisely. That means sum of the squares of each row is 1, and sum of the products of any row with the corresponding elements of any other row is 0. That means sum of products of elements of any two distinct rows or columns is 0. Suppose you take this, right? You take suppose 0 matrix. Suppose 3 by 3 0 matrix. Is it orthogonal? The answer no, because look at this row. Sum of the squares of the elements. What is the definition? It should be 1, but it is equals to 0, not equals to 1. What is my definition? Sum of the squares of the elements of each row should be 1. But what happens for this matrix? Sum of the squares of the first row is equals to 0, which is not equals to 1. Hence, it is not orthogonal matrix. Right? Suppose you take this identity matrix. Is it unitary? Is it orthogonal? Sorry. Is it orthogonal? Yes. Look at the first row. Sum of the squares of the elements of first row. This is 1. Sum of the squares of the elements of the second row. This is also 1. Sum of the elements of, this is 1, sorry. Sum of the elements of squares of the third row is also 1. Right? And look at the product. This into this. Product, sum of the products of the any two distinct rows or columns is equals to 0. This means you know that 1 into 0 plus 0 into 1 plus 0 into 0. What is this? 0. Similarly, look at these two rows. 0 into 0, 1 into 0, 0 into 1. This is 0. Look at these two rows. Look at this first row and third row. That means 1 into 0, 0 into 0, 0 into 1. That means sum of products of any two distinct rows or columns with the corresponding elements is 0. And sum of the squares of each row or column, of course, once you calculate this idea along the column, you can get the same answer. 1 square plus 0 square plus 0 square is 1. 0 square plus 1 square. What is this? 1 square plus 0 square plus 0 square is along the column also same result you get. Understand? 0 square plus 1 square plus 0 square is equals to 1. What is this along this column? 0 square plus 0 square plus 1. 1. So if you calculate along the row or column, you can get the same result. So what is my definition? My definition is sum of the squares of the elements of any row or column is 1. Sum of the products of any two rows or columns is 0. Two distinct rows. In fact, two distinct rows or columns are 0. Right? Or else you can check this idea. Or else you can check this A into A transpose into A equals to I. It's also trivial. You can check it. Or else what you do? What you do is that calculate A into A transpose. This is a long procedure. Understand? So suppose you take A into A transpose. What is this? 1 into 0, 0, 1, 0, 0, 0, 1. What is A transpose? Same identity matrix. Identity matrix into identity matrix. You're going to get identity matrix. Similarly, A transpose into A means what? I transpose into I. That is nothing but I into I. That is equals to I. So therefore, this also another method. But this is very easy method. Sum of the squares of the elements of each row or column should be 1. Suppose you take this. Suppose you take A equals to 0, 1, minus 1, 0. Is it orthogonal matrix? Look at this first row. Sum of the squares of the first row is nothing but what? 1. Sum of the squares of the second row, this is also 1. Okay. Next, look at the sum of the products of this first row and second with the corresponding elements of the second row. What happens? 0 into minus 1 plus 1 into 0 is equals to 0. Therefore, satisfy the condition. Therefore, hence it is orthogonal. Right? Suppose you take this is equals to cos theta, sin theta, minus sin theta, cos theta. Is it orthogonal? Anybody?
Yes.
Right? So therefore, cos square theta plus sin square theta is equals to 1. This also minus sin square theta
Whole square
plus
plus
cos square theta equals to 1. Therefore, sum of the products of the sum of the squares of the elements of each row is 1. And look at the second condition. Sum of the products of the elements of the row, any row with the corresponding elements of any two other row. Between other row, sin theta, cos theta is equals to 0. So it satisfies the condition. Therefore, it is orthogonal matrix. It is orthogonal. Right. Next, fifth one. Suppose this, you can take this a equals to 2 0 0 1. Is it orthogonal? The answer no. Right? Look at this row. 2 square plus 0 square is equals to 4, which is not equals to 1. So it fails to satisfy the first property. Hence, it is not orthogonal. Is it clear? Suppose we take this a equals to 0 1 0 0 1 0 minus 1 0 1 0 0. Is it orthogonal? Anybody?
Yes.
Yes. Right. Look at this row. 0 square plus 0 square plus 1 square is equals to 1. 0 square plus minus 1 whole square plus 0 square is equals to 1. Look at this row. 1 square plus 0 square plus 0 square is equals to 1. So sum of the squares of the each row or column is 1. And look at the second idea. So, second condition. Look at the first and second row. Sum of the products of the elements of any row with the corresponding elements of any other row. It should be 0. Look at this one. Look at this one. 0 into 1 plus minus 1 into 0, 0 into 0, that is equals to 0. And look at first and last. Look at first and second over and first and last over and first and last, or second and third. This one. So what is this? 0 into 1 plus minus 1 into 0. Next 0. Already we have done it, right? In the next first and third. First and third actually. What is first and third? 0 into 1 plus 0 into 0, 1 into 0, this is equals to 0. So therefore it is orthogonal. Right? Next is, look at the algebraic properties. Suppose you take A is orthogonal, B is orthogonal. Both are orthogonal matrices. Question is, does it mean that whose sum is it orthogonal?
No, sir.
No. So can you give example? Look at this identity matrix. It's an orthogonal. We have seen. Look at this matrix. It's also identity matrix. So we have seen that both are orthogonal. Clearly, both are orthogonal matrix. So no, both are orthogonal matrix. We have seen every identity matrix is orthogonal matrix. Right? Look at the sum. What is my sum? 2 0 0 0 2. So it fails to satisfy the first property. So 2 square plus 0 square is equals to 4, which is not equals to 1. Hence it is not orthogonal. Right? In general, sum of, that means what? In general, what you conclude? In general, sum of orthogonal matrix, any two orthogonal matrix, sum of any two orthogonal matrices need not be orthogonal. Right? Why it fails to satisfy the orthogonal? Some of the orthogonal may not be orthogonal. You know, look at this. Suppose A and B are orthogonal. That means A into A transpose into A equals to A transpose into A equals to identity matrix, and B into B transpose and B transpose into B should be I. Is my definition. Look at the sum. Look at the sum. Is it identity matrix? Look at it. A plus B. Right? What is this? A transpose plus B transpose. Transpose of sum is equal to sum of the transposes. And matrix addition satisfies distributive property with respect to multiplication. Matrix multiplication is distributive over addition. Sorry, A into A transpose, A into B transpose, B into A transpose plus B into B transpose. So therefore, A into A transpose, we have seen that actually it is I using this property. AB transpose, B into A transpose plus identity matrix. Right? In general, it cannot be I. Right? In general, it cannot be I. But if you take the condition, this is equals to I if and only if AB transpose plus B transpose, B into A transpose plus I plus SI equals to identity matrix. If it is equals to identity matrix, this answer is right. So that means matrix addition. Matrices is nothing but what abelian group. Therefore, in fact it's a group. Therefore, it satisfies cancellation law with respect to addition. So therefore, this cancel. That means AB transpose A into B transpose is equals to plus B into A transpose plus identity matrix is equals to 0. In general, some may not be orthogonal, but if you take this condition, A plus B, A into B transpose plus B into A transpose plus identity matrix is equals to 0. If you take this additional condition, A plus B should be orthogonal matrix. Understand? That means A plus B orthogonal matrices. If A and B are orthogonal matrices of same order, in fact, otherwise some may not be meaningful. Is orthogonal if and only if AB transpose B into A transpose plus identity matrix is equals to 0. In general, some may not be orthogonal, but if you take this additional condition, A into B transpose plus B into A transpose plus I equals to 0, if you take this additional condition, this sum would be orthogonal. Is it clear? No, is it clear?
Yes, sir.
Right. Now, look at the product. Suppose A and B are orthogonal matrices. What about this product? Is it orthogonal?
Orthogonal.
Yes. Look at the product. What you are given, actually you're given that A and B are orthogonal. That means A into B transpose into A equals to identity matrix. And notice that B also orthogonal. B into B transpose into B should be identity matrix. We'll check whether AB is orthogonal or not. So therefore, look at the definition. AB whole transpose, that is equals to AB. Reverse law for the transpose. B transpose into A transpose. Matrix multiplication is associative. So this can be rewritten as B into B transpose into A transpose. Therefore, A into what is this? Identity matrix. Because this idea. So A into A transpose, that is equals to identity matrix. Similarly, one can check B transpose A into B whole transpose into AB is equals to identity matrix. Therefore, there is no problem with the product. Product is always finite product is always orthogonal. That means in general, product of any two orthogonal matrices is orthogonal using the associative property and definition of orthogonal. Right, in general, this is true. Right? And look at the scalar product. Look at the scalar product. If A is orthogonal, if take A, K is any scalar, does it mean that what about the scalar product? Is it orthogonal?
No.
Yeah, in general, no. Suppose you take this, suppose you
K is
take A is
equal to-
equals to identity matrix, K equals to 2. If you take
One.
K equals to 2, or if you take K equals to 1, obviously it is
Possible.
orthogonal. If you take K equals to 2, what happens? K into A, that is equals to K is 2 into identity matrix. That is equals to 2 into 1, 0, 0, 1. For sake of our convenience, I'm going to take K should be 2 cross 2 matrix. N equals to 2. That means this is equals to 2, 0, 0, 2. The sum of the squares of this first row is equals to 4. It should not be equals to 1. Therefore, it is not orthogonal. So K into A is not orthogonal.
K equal to 1 in applied case.
Yeah, but in general, I'm telling you that in general,
Okay.
K into A may not be orthogonal, right? But look at the idea. Actually, if you take this, what is the problem behind this? Once you take, what is the problem here? K is orthogonal matrix. K is any scalar. Take. What is the problem? Look at the definition. K into A whole transpose. Where you're getting scalar product may not be orthogonal. What is the problem behind this? Look at this. K into A as it is. K into A whole transpose is equals to K into A transpose. That this can be rewritten as K into K square, K into A transpose. That means K square into I. In general, K square into I cannot be identity matrix. In general, this is may not be true. But this is true if K square into if only if K square into I is equals to I. Yes or no? But this is if only if K square into I equals to I means what? What does it mean by this? K square into, if you take this is a identity matrix for for loss of general, you can take any 3 by 3 or 4 by 4 matrix. What is this? What is this? K square is 0, 0, 0, K square, 0, 0, 0, 0, K square, 0, 0, 0, 0, K square, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Therefore, two matrices are equal if only the corresponding elements are same. What is the first 1, 1 entry? 1, 1 entry here. K square equals to 1. So K square equals to 1. If and only if, if you take it is in general, this result hold because I'm restricting my K should be any scalar. I don't know whether it is a real scalar or complex scalar. But when I restrict K is a real scalar, K equals to plus or minus 1. Understand? K equals to plus or minus 1. When I restrict K is a scalar, which is a real scalar, if this is true, or else if you take any K complex scalar as it is, K square should be 1. Understand? In general, K into A may not be orthogonal matrix, but if you provide K square equals to 1, if you take as any scalar in such a way that K square whose square is equals to 1, automatically it is orthogonal matrix. Suppose you take this. Just now we said, no, suppose you take A is orthogonal orthogonal? Suppose I am going to give k equals to 1. What is k into a? 1 into a. That is nothing but what? 1 into a is equals to a. We have shown already. Look at the first lecture. A is already we have seen that a is what is a? A is orthogonal matrix. Therefore, k into a is orthogonal. As you know that a is orthogonal, therefore k into a must be orthogonal. Suppose if you take k equals to -1, it satisfies the property k square is equals to 1. Therefore, what about k into a? K into a is equals to -1 into a. That means what? Minus a. It is also orthogonal. It is also orthogonal. Therefore, whenever k is orthogonal, if you take a scalar in such a way that whose square equals to 1, then k into a should be orthogonal matrix. Is it clear? In general, may not be, but if you take provide a scalar in such a way that whose square equals to 1, that is orthogonal. Is it clear? Is it clear, Andy? Hello?
Yes, sir.
Yes. Suppose this, you take this, another idea. What about the transpose? Suppose you take this orthogonal matrix. Suppose you take the transpose. Doesn't mean that. What about the transpose of this? Is it orthogonal? Is it orthogonal? Look at the definition. A transpose into A transpose whole transpose, that is equals to A transpose into A. What is my orthogonal matrix? Orthogonal matrix implies A into A transpose equals to A transpose into A equals to identity matrix. Using that idea, that is equals to I. Similarly, A transpose whole transpose into A transpose, that is nothing but A transpose whole transpose is equals to A, and that into A transpose. A into A transpose is equals to identity matrix. Therefore, satisfying the condition, therefore it is orthogonal matrix. That means, what do you conclude? In general, transpose of orthogonal matrix is always orthogonal matrix, right? Now, suppose A is orthogonal. What about its determinant? Generally, suppose A is orthogonal, you assume that A is orthogonal, that means A into A transpose is equals to I in particular. A into A transpose should be I. And look at the det property. Det of A into A transpose is equals to det of I. But det of I is equals to identity matrix, that is equals to 1. So det of AB, this property, we'll see later. Det AB is equals to det A into det B. Use this property. Det A into det B is nothing but det A into det A transpose, that is equals to 1. Later we'll see that det A is equals to det A transpose, both are same. Therefore, det A into det A equals to 1. That means det A square equals to 1. Right? So that means det A should not be non-zero. Right? Det A should not be non-zero. Yes or no? If det A is 0, 0 square could not be 1. Therefore, det A should not be non-zero. So therefore, whenever A is orthogonal matrix, automatically that will implies that det square A should be 1. Det A square is equals to 1. Or else you can take det A square is equals to 1 means what? Det A is equals to plus or minus 1. That means what? Det A square, det A should not be 0. That means what? A is a non-singular matrix. That means what? Any orthogonal matrix, what is my notice? Any orthogonal matrix is a non-singular matrix. Every orthogonal matrix is a non-singular matrix. So that is, suppose you take 0 matrix, suppose you take this matrix, suppose you take this 1 0 0. Is it orthogonal? No. What is my det? What is my det? Det A is equals to 0. Therefore, it is non-singular matrix. Therefore, it is not orthogonal. matrix. You can use that property also. You can take this as a definition also. Understand? No, every orthogonal matrix is non-singular matrix. Once it is non-singular matrix, we can talk about the inverse. Understand? If A is orthogonal, once it is orthogonal matrix, so it is always invertible matrix because it is non-singular matrix. Once it is non-singular matrix, so it inverse exists. What about the inverse? Does it mean that whose inverse is also orthogonal? Is it orthogonal matrix? So look at the definition actually. Once A is orthogonal, A into A transpose into A equals to identity matrix. That means A into A transpose, you take the whole inverse, because already you know that A is orthogonal means what? A is invertible matrix because A is non-singular matrix. Once A is orthogonal matrix, automatically det A is non-zero matrix. Non-zero. Det A is non-zero number. That means A is non-singular matrix. That means A is invertible matrix. We'll see later. Once det A is non-zero, it should be invertible matrix. So we can talk about the inverse. You can take the inverse on both sides. Inverse of, reverse product of inverse. That means what? A transpose whole inverse. That means A inverse. A inverse into A transpose whole inverse is equals to inverse of I equals to I. So this, what is the inverse of A transpose? Transpose of the inverse. I've seen already. What is this? Inverse. Inverse of the transpose is equals to transpose of the inverse. It's equals to I. Therefore, A inverse whole transpose into A transpose A inverse equals to A inverse into A inverse whole transpose is equals to identity matrix. So this tells you that A is ortho, A inverse is orthogonal matrix. So what you conclude? So conclusion is inverse of orthogonal is also orthogonal. Right? So inverse of orthogonal is always orthogonal matrix. Now look at the cardinalities. See, suppose actually, suppose your orthogonal matrix. Suppose 1 cross 1 orthogonal matrix. How many 1 cross 1? How many 1 cross 1 orthogonal matrix over a field R? How many orthogonal matrices of order 1 cross 1, suppose over field R. Or else you can take this. See, this is same as saying that, or else you take this 1 cross 1 matrices over R in such a way that orthogonal matrix. Orthogonal matrix. That means what? A is orthogonal. What is the coordinate of this? Anybody? What is the coordinate of this?
2, sir.
Yeah.
1 minus 1.
1 minus 1. Good. Suppose you take any matrix which is an orthogonal. Very good. Good idea. So that means you take any element we take in a collection, yes, collection set S, that should be orthogonal. That means A into A transpose is equals to A transpose into A equals to I. But what is my A? A should be 1 cross 1 matrix. So for loss of generality, you can take A is like this. A equals to 1 cross 1 matrix. A is any real number. That means A into A transpose is equals to A transpose into A equals to identity matrix. That means this is A as it is, but this transpose of the singleton is as it is itself. What is this? A into A equals to identity matrix. The product. What is the product? Anybody? A square is equals to, in particular, identity matrix. But what is my identity matrix? Here 1 cross 1 matrix. What is my identity matrix? 1 cross 1 matrix, because A is a 1 cross 1 matrix. A is an element of S. Once A is an element of S, A should be 1 cross 1 matrix over a field R. So therefore, this is actually, what is the identity matrix? What is the identity matrix of order 1 cross 1? Only one. Only one. Therefore, two matrices are equal. This is a matrix. This is a matrix. This is a matrix. Two matrices are equal if only the corresponding elements are same. That means A square equals to 1. Therefore, what is my A? A is a real entry. Therefore, A equals to plus or minus 1. Right? So, what are my possibilities of A? What is my matrix? Actually, given matrix is actually what? This matrix. We assume that this is a matrix, orthogonal matrix. So, what are the possibilities of A? So, the possibilities are A can be one matrix, singleton one matrix. A can be singleton minus one matrix. So, what is the possibility for A? There are two possibilities. So, therefore, what is the coordinate of S now? 2. Is it clear? Hello? Is it clear, Andy?
Yes, sir.
Yes. So, there are only two possibilities. Suppose, same question. Suppose I'm going to give a question. Set yes, a collection of orthogonal matrices of order 2 cross 2 over a field R. Now tell me, what is the coordinate of S? Anybody? What is the coordinate of this? Anybody? Already I given example just now. You take this matrix. You take this matrix. Suppose you take A equals to cos theta sin theta minus sin theta cos theta. You take theta is a real number. Don't take it. It is a complex number because I want the matrix to be, real matrix. The entries are real numbers. So is it orthogonal? Anybody? We have seen that actually sum of the squares of the first row is 1. Sum of the squares of the second row also 1. And product of the any two distinct rows, it is 0. So therefore, it is orthogonal matrix. Now my question, how many such matrices are there? There are uncountable matrices because actually once you give me theta, I can get A. Once you take theta equals to from pi by 3, you get orthogonal matrix. Once theta equals to pi by 3, you can get orthogonal matrix. Once theta equals to pi by 2, you can get another orthogonal matrix. You take theta equals to pi by 6, you can get another orthogonal matrix. So given any r, given any theta, we get how many orthogonal matrices over a field R? Anybody? How many orthogonal matrices? Hello, how many orthogonal matrices? Give me any theta, give me any real number, we can get orthogonal matrix. Now, how many orthogonal matrices?
Infinite.
Uncountable many, because the R is uncountable, right? You get uncountable many. So what is the coordinate? Continuum. Right? That means in fact it is infinite or continuum. Infinite, not infinite. Sorry. Is it clear? Anybody? Now you can extend this idea to any matrices. Any matrices. That means in fact we take any matrices of order any order. That means 3 cross 3, 4 cross 4, 5 cross 5. Right? You can extend this idea. Is any matrix of 3 cross a matrix. These are orthogonal. What is the coordinate of this? Anybody? Infinite. Why? Because I can give this matrix cos theta 0 sin theta 0 1 0 minus sin theta 0 cos theta. Now is it orthogonal? Theta is a real number. Is it orthogonal? Anybody?
Yes, sir.
Yes. Because sum of the squares of the element is 1.
1.
This also 1. This also 1. And sum of the products of any two distinct rows is 0.
0.
Therefore, it is orthogonal. Therefore, once you give me theta, we can get any orthogonal matrix. So it is infinite. How many thetas? Uncountable many. It is infinite. Right? Now, I can restrict my set to 2 cross 2 matrices or n cross n matrices. A is orthogonal. I restrict my orthogonal matrix to which the entries of the orthogonal matrices are suppose you take 0, 1. What is the coordinate of this? Anybody? Suppose you take 0. What is the coordinate of this? Anybody? That means you take any entry that is 0. What is the coordinate of S? Any matrix you take in S, yeah, 0. Who said?
Satish.
Good, very good. So that means that matrix whose entry is 1. Each entry is 1. That means 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Is it orthogonal? Anybody? Is it orthogonal? No, right?
No, sir.
So therefore, coordinate of S is 0. But if you take the same set, but by adding a different element, A is orthogonal. Suppose my entries are 0, 1. What is the coordinate of S? Anybody?
1, sir.
Only 1? Only 1? Yeah. Suppose you take any matrix that is orthogonal. That you take any matrix in S. That should be orthogonal. That should be orthogonal matrix. That should be orthogonal matrix. Right? Now my question, what are the entries of this? This is my first row. This is 1, 1 entry. This is 1, 2 entry. This is 1 n entry. Now, what is my first condition of the orthogonal matrix? Sum of the squares of the squares of the elements of any row or any column should be 1. So A1 and A11 entry can be filled by 0 or 1. Yes or no? First you fix 1. First you fix 1, Amma. First you fix 1 because actually I need, that sum of the squares of the elements of any row or column that should be 1. So first you fix 1. How many ways can 1 can be filled?
N ways, sir.
N ways.
N by
N ways.
N ways.
N ways, right? So therefore it is n ways. Suppose you fix here 1. Suppose without loss of generality is 1. So this is n ways. Now remaining entries. What are the remaining entries? See, suppose I filled this 1, 1 entry as 1. What are the remaining entries? Anybody?
Zeros.
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 Zeros. This is 0. This is 0. This is 0. Yeah. First row can be filled by n ways. Yes or no? Similarly, what is my second row? This is A21 entry, A22 entry, A23 entry, going on A2n entry. Now my question: in how many ways A21 entry can be filled?
N minus 1, sir.
N.
A21 entry. I'm asking A21 entry.
N, sir.
A21 entry. How many ways
Two
can
ways.
A21 entry be filled?
0, sir. Only one way.
Only one way. A21
0.
entry can be filled by 0 only because. Yes or no? Because
31.
look at the column. Look
Yeah.
at the column. Sum of the squares of the elements of first column is 1, right? So if it is non-zero, suppose it is filled by 1. What happens? 1 square plus 1 square. It is 2, right? Yes or no? So therefore it could not be 1. It could not be 1. So therefore it should be only one way. It should be 0. It should be 0. Yes or no? Now tell me, how many ways? See, I want to be that each sum of the squares of the any elements of any row should be 1. Therefore, how many ways can one be filled in second row?
N minus 1.
Yeah. So this, there are n minus 1 entries. So therefore, 1 can be fixed here. 1 can be fixed here. Remaining entries are 0. 1 can be fixed here. Remaining entries are 0. 1 can be fixed here. Remaining entries are 0. So therefore, how many ways? How many ways? N minus 1 ways. Yes or no? This is already fixed. 0 is already fixed. 0 is already fixed. So this is 1, 2, 3, 4, 5, n minus 1. So how many ways? N minus 1. Similarly, here 0, automatically this should be 0. So without loss of generality, it is 1. Suppose you take this is 1. Now what is the entry of this? 0. So in how many ways this A33 entry, A34 entry, filled by 1? How many ways can the third row can be filled by 1?
N minus 2.
N minus 2. Similarly, how many ways? 1 ways. So therefore, now tell me what is the cardinality of this? Therefore, work is completed. Therefore, fundamental principle for multiplication. Therefore, this is n factor. Is it clear? Is it clear? Any doubts? Tell me.
Okay, sir. Okay.
Okay. Now, if I fix the elements by 0, suppose take example. Suppose A is orthogonal. If you fix my elements, if you fix the elements 0, 1, minus 1. Now tell me what is the cardinality of this? Yeah. Take any matrix that should be looking like this. Yeah, tell me. This A11 entry, A21 entry, A12 entry, A13 entry, A11 entry. Now tell me, in how many ways can 1 entry can be filled?
2 power n
First-
factorial, sir. Okay.
Yeah, I don't know the answer, but yeah, now my question. First you fix 1 or minus 1? 1 or minus 1? How many ways can 1 and minus 1 filled? How many ways can 1
power
and minus 1 be filled? You
2
know,
power
this can be filled, yeah, this can be filled by 1 or minus 1. Because I need to actually look at the first property. Look at the first property. Right? Sum of the squares of the elements of any row is 1. Therefore, a 1 entry can be filled by 1 or minus 1. Here 1 entry can be filled by 1 or minus 1. Here 1 entry can be filled by 1 or minus 1. Here 1 entry can be filled by 1 or minus 1. So therefore, this 1 entry, can be filled by 1 or minus 1. Now tell me, in how many ways can one row, first row can be filled? So here 2 ways, are 2 ways. Yes or no? See, ఇక్కడ మీరు 1 ఫిక్స్ చేసిరు అనుకోండి, ఇక్కడ మళ్ళీ 1 రాయదు కదమ్మా. ఎస్ నో? ఎందుకు సమ్ ఆఫ్ ద స్క్వేర్స్ ఆఫ్ ద ఎలిమెంట్స్ ఏం కావాలి? 1 కావాలి కదా. ఎస్ నో? సో ఇప్పుడు మీరు 1 ఇక్కడ ఫిక్స్ చేశారు అనుకోండి, 1 ఆర్ మైనస్ 1 ఫిక్స్ చేశారు అనుకోండి, కంపల్సరీ 0 కావాలి. Understand? So this work can be done. This first row can be filled by 2 ways. That means 2 plus 2 plus 2 plus 2 ways. Because na work enti first row fill cheyadame. Second row kaadu right now. First row ne. My work is to complete the only. Look at the first row. In how many ways can first row can be filled by using these entries 0, 1, minus 1 in such a way that A is a orthogonal matrix. So 2 power n only. It is not multiplication. Remember, it is not multiplication. 2 plus 2 plus 2 plus 2 plus 2. Now, what is this? 2 power n? 2 n into 2.
2n.
Yeah, n into 2, right? Right? Now, without loss of generality, I fix here 1. Here fix are 1 or minus 1. Amma. First 1 entry 1 or minus 1 అనుకోండి suppose. This is 0. Without loss of generality, this is 0. This is 0. Now tell me, what is the entry of this? What is A21 entry? 0. What is A21 entry? Automatically it is 0. Because sum of the squares of the first column should be 1. So therefore this should be 0. Now tell me, how many ways can second row be filled by using the entries 0, 1, minus 1? Tell me more. చెప్పాను కదా, ఇది 2 ways, are 2 ways, are 2 ways, are 2 ways. 2 plus 2 plus 2 plus 2 plus 2. How many ways? N minus. That means what? 2 into n minus 1. So second row can be filled by in how many ways? 2 into n minus 1. Second row can be filled by using the entries 0, 1, minus 1 in how many ways? 2 into n minus 1 ways. Similarly, this 0, 0, this can be filled by three ways. 3, 4 going on 3n. So this is nothing but 2 into n minus 2. Similarly, this is what is this? 2 into 1. That means what? 2 into, so total work, what is this total work? 2 into n, 2 into n minus 1, 2 into n minus 2, going on 2 into 1. What is this? 2 power n into n minus 1 into n minus 2 into n minus 3 into 2 into 1. What is this? In factor.
2 power n into n factorial.
2 power n into n factor. So this is the answer. Is it clear? Is it clear, all of you?
Yes, sir.
ఇదే ప్రాబ్లం నేను కొంచెం రిప్లై చేసినప్పుడు సెట్ ఆఫ్ ఆల్ ఆర్థోగోనల్ మ్యాట్రిక్స్ whose entries are 0, 1, minus 1, 2 అని ఇచ్చాను అనుకోండి. Now tell me, what is the coordinate of this? 0, minus 1, plus 1, 2. ఇప్పుడు చెప్పండి అమ్మా, what is the coordinate of this?
Same sir, 2 power n into n factorial.
Same thing, because it is not needed, right? 2 entries not needed, because actually 2 entries is not useful, right? Because actually what is my property? Sum of the squares of the elements of each row or column should be 1. Sum of the products of elements of any row with the corresponding elements of any other row is 0. Therefore 2 entries not needed, right? If you fix 2 entries somewhere, it fails to satisfy the first property. Sum of the squares of the elements of the any row or any column should be 1 actually, but it fails to satisfy that property. Therefore 2 is not needed. 2 is not necessary. Therefore, in how many ways can filled by the orthogonal matrix using this entry 0, 1, minus 1, plus 2? So coordinate of S is 2 power n into n factor only, because I need only these entries are needed. I don't require this 2 entry. Therefore, what is the coordinate of S? 2 power n into n factor. That's it. Now, is it clear?
If the same question, instead of asking cardinality, if we ask whether it is orthogonal or not, so our answer is not orthogonal.
See, I'm looking at the orthogonal collection of orthogonal matrix. I'm looking at the orthogonal matrices. I'm not asking that whether it is orthogonal matrix or not. Suppose you're given a matrix, like this, right? You are given a matrix like this, right? Whether it is orthogonal or not means check, look at the first row, look at the square, sum of the squares of the elements of this row. It is actually 4, it is not equals to 1, therefore it is not orthogonal. But I'm not looking for the whether it is orthogonal or not. I'm looking for the collection of all orthogonal matrix whose entries are 0, 1, minus 1, plus 2. I'm looking at all collection of all orthogonal matrices, not only single matrix. మీరు మ్యాట్రిక్స్ ఇస్తే అది ఆర్థోగోనల్ కాదా చెక్ చేయండి. ఇక్కడ అడిగింది ఏంటమ్మా, కార్డినాలిటీ అంటే ఏంటి? టోటల్ ఆర్థోగోనల్ మ్యాట్రిక్స్ ఎన్ని ఉన్నాయి ఈ ఎంట్రీస్ తోని అంటున్నాడు. ఈ ఎంట్రీస్ తోని.
Got it.
Yeah. Now, unitary matrix. Right? What's the time? Right now, 7:20. సరిపోదు అనుకుంటాను. So, any doubts? Any doubts? Till now, any doubts? Sharp వెయిట్ చేస్తున్నారు సార్. హలో
సార్, కంటిన్యూ సార్.
సార్ వెయిట్ చేస్తున్నాడు సార్.
No sir, continue 10 to 15 minutes.
Okay. So unitary matrix. So A is a square matrix. A is a unitary matrix. If only A into A theta into A is equals to identity matrix. This exactly precisely, what is this ijth entry of this? Ijth entry of this is equals to ijth entry of these products and ijth entry of this. This is true for every ij. That is exactly precisely, ijth entry of the product is equals to sum of the product of the elements of ikth entry of A and kjth entry of A theta. That is equals to sum of the products of the elements of ijth entry of A theta, sorry, ikth entry of A theta and kjth entry of A. That is equals to canonical delta. This is true for every j. Right? What are this? This is nothing but summation A equals to 1 to n ikth entry of A. What is this? A bar whole transpose kj. Kjth entry of the transpose of the conjugate. This is k equals to 1 to n. A bar whole transpose ikth entry of this into kjth entry of this is equals to canonical delta. This is true for every ij. But this is same as saying that k equals to 1 to 1 ikth entry of this kjth entry of the transpose is equals to jkth entry of A bar. By definition. Right? This is nothing but what? Kith entry of this into this is equals to canonical delta. But this is same as saying that summation k equals to 1 to n ikth entry, this is as it is, keep as it is. Jkth entry of A bar is nothing but conjugate of jkth entry. Conjugate of jkth entry by definition. Right? This is exactly same as saying that, but when the canonical delta works, whenever j equals to 8, it works, otherwise it is equal to 0. So using this idea, this if one only, j equals to 1. Whenever j equals to I, what happens? Whenever j equals to I, this is ik, k bar in particular, this is equals to 1 and k equals to 1 to n, ikth entry of this, jkth entry of the conjugate of the jkth entry, this is 0 for j not equals to I. Whenever j equals to I, this is 1 or else this is 0 using the canonical delta. That is exactly precisely k equals to 1 to n a into a, z into z bar is equals to mod z square. For every I or for every j. K equals to 1 to n ik jkth entry of jkth entry of the bar, that means bar of the conjugate of the jkth entry, this is 0 for every j not equals to I. That means what you conclude? Sum of squares of moduluses. What is this actually? This stands for modulus. Sum of squares of moduluses of elements of any row or column is 1, and sum of the products of right? This is JK. Okay, that's it. This is JK. Yeah. Sum of the products of elements of any row or column with the corresponding elements with the corresponding conjugates. What is this? This is nothing but conjugates, you know. This is conjugates. So, you know, corresponding conjugates of elements of any other row, because J not equals to I. Any other row or column is 0. That's it. Right? This is definition. This is a definition. Sum of the squares of the modulus of any elements of any row is 1, and sum of the products of elements of any row with the corresponding conjugates of elements of any other row is 0. This is a definition actually. And look at my example. Suppose you take this a 0 matrix. Is it a unity matrix? No, because look at the first row. Sum of the moduluses of the squares of the elements is nothing but 0. 0 cannot be 1. Therefore, it is not unitary matrix. Not unitary matrix. Let's suppose you look at the identity matrix for sake of our convenience, for understanding purpose. Take identity matrix of n by n, or else you can take any 2 by 2 or 3 by 3 matrix. Is it unitary? Yes, because look at the first row. Sum of the squares of the moduluses of each row is actually 1. Look at the second row. Sum of the squares of the modulus of the each element is 1. Look at the third row. Sum of the squares of the elements of the third row is equals to 1. And look at the sum of the products of these elements is 0. Conjugates. See, look at the what is the conjugate of this? You know, conjugate of 0 is nothing but 0 because they are real entries now. You know, 0 bar is equals to 0, therefore it is 0. Now look at this 0 0 bar, 1 0 bar, plus 0 1 bar. What is this? 0 itself. Look at the first and last. 1 0 bar, 0 0 bar, 0 1 bar. What is this? 0. Therefore, it satisfies all conditions, hence it is unitary matrix. Right? Suppose you can take this. A is equals to I 0 0 I. Is it unitary? The answer is yes, because sum of the squares of the modulus of each entry of any row. Modulus of I is nothing but 1. 1 square is nothing but 1. This is sum of the squares of the modulus of each entry is equals to also 1 square, that's equals to 1. What is the product? I 0 bar, 0 I bar. I 0 bar is nothing but 0. 0 and I bar is nothing but minus I, that is nothing but 0. Therefore, satisfying the second condition, hence it is unitary. Right? Suppose look at this. 0 e power I theta 0 0 and 0, or else for sake of our convenience you can take only 4 by 4 matrix. So 0 e power minus I alpha 0 0 I, or else it fails to satisfy that. So 0 0 0 0 I and 0 0 minus I 0, where alpha and theta are the real entries. Now tell me, is it actually after unitary matrix? The answer yes. Look at the first row. Sum of the squares of the modulus of the squares of the modulus of each row. What is e power I theta? Modulus, it is a Euler form. E power I theta, whenever theta is a real number, cos theta plus I sin theta. Euler form, is nothing but what? 1. 1 square is nothing but 1. This is minus e power I theta. Modulus whole square, 0 square, modulus, 0 square, modulus of 0 whole square. That is equals to e power I alpha. Alpha is a real number. Therefore, again, it is a inverse of e power I theta. That is nothing but again 1. 1 square is nothing but 1 itself. Right? Look at this sum of the squares of the third row, modulus of the third row. That is equals to 1. Sum of the squares of the modulus of fourth row. It is also 1. To satisfy the first property. What is the second property? Of course, it satisfies this property also, because this into this 0, this into this 0, this into this 0, this into this 0. Similarly, this 0. Similarly, 0. Similarly, first and third is also 0. First and fourth is also 0. Therefore, it satisfies all property, hence it is unity. Now tell me, how many unitary matrices are there? Anybody? Of order 4 by 4? How many unitary matrices? Huh? Infinity. That's it. Infinity. Similarly, second order also same, right? Second order also same, right? Suppose you take this. No need to take minus, you take plus also, okay. But theta is a real number. Is it unitary? The answer is 1 square is equals to 1. 0 square plus e power I theta whole square is equals to 1. So satisfy the first property. What is the second property? E power I theta 0 bar plus 0 into e power I theta bar, that is equals to 0, 0, that is equals to 0. So therefore it is unitary. Now how many such type of matrices are there? How many such type of matrices? 2 plus 2 matrices. Infinity. Right? Now, suppose you take this. A is equals to cos theta, sin theta, minus sin theta, cos theta. Theta is a real number. Is it unitary? Anybody? Theta is a real number. Cos theta is always a real number. Cos square modulus of x square is nothing but x square itself. N square theta, that is equals to 1. Because theta is a real number. Right? This is nothing but modulus of sin theta whole square plus modulus of cos theta whole square, that is equals to sin square theta plus cos square theta, that is equals to 1. So satisfy the first property. What is the second property? 0. Cos theta into minus sin theta bar sin theta cos theta bar. What is this? Cos theta. Sin theta is a real number. Sin theta is always a real number. Because theta is a real number means sin theta is always a real number. So once it is real number, z bar is equals to z bar is equals to z sin theta into cos theta, that is equals to 0. Therefore, it is also unitary. Right? Now tell me, you look at the properties. You take A and B are unitary matrices. What about the sum? Is it unitary? The answer? No, right? Need not be, right? You take this same A is in any matrix. For loss of generality, you can take identity matrix. B is equals to identity matrix. Clearly, A and B are unitary matrices. But what about the sum? Sum is equals to 2, 0, 0, 2. Is it unitary? No. because sum of the squares of the modulus of the each row should be 1, but it fails to what to satisfy the first property. Therefore, it is not. It is to satisfy the first property, hence it is not. It not be orthogonal, unitary matrix. In general, no, but no, that means what? In general, sum of any two unitary matrices need not be unitary. But if you take the additional condition, what is the problem here? Look at the problem. You take A and B are unitary matrices. That means A into A theta into A equals to identity matrix, and B into B theta into B equals to identity matrix. Look at the sum. We are getting a problem. That means A plus B theta, A plus B into A theta plus B theta. We have seen the properties of the Hermitian matrix. That means transpose of the conjugate. A into A theta plus A into B theta, B into A theta plus B into B theta. That means this is I plus A into B theta, B into A theta plus I. That means, in general, actually what I need this to be identity matrix. But in general, this not equals to I in general. But if you provide this equals to I, if and only if this total matrix should be identity matrix. So identity matrix cancel because matrices with respect to addition is an abelian group. That's why cancellation loss. So therefore, this if and only if A into B theta plus B into A theta plus I equals to 0 matrix. That means if A and B are unitary matrices, then A plus B is unitary if and only if A into B theta, B into A theta plus identity matrix is equals to 0 matrix. In general, no, but if you take A into B theta plus B theta into A theta, B into A theta plus identity matrix is equals to 0 matrix. Right? What about the difference? Sum of matrices, sum of unitary may not be unitary, but what about the difference? Take A and B are unitary. What about the difference of these matrices? Is it unitary? Does it mean that is it unitary? The answer no. In general, so both are unitary matrix. Clearly, both are unitary matrix. Unitary matrix. But what about the difference? The difference is equals to 2, 0, 0, 2. It fails to satisfy the first property. Modulus of 2 square plus 0 square is equals to 4, which is not equals to 1. Hence, it is not unitary. Right. Next, what about the product? If A and B are unitary matrix, what about the product? Does it mean that A into B unitary? Look at the definition. AB into AB whole theta is equals to AB is B theta into A theta. That is equals to B into B theta into A theta. That is equals to this identity matrix into A theta. That is equals to A into A theta. That is equals to identity matrix. Similarly, this can be rewritten as this can be is equals to identity matrix. So therefore, in general, so this is S orthogonal matrix. That means product of any two unitary matrices is unitary. Right? Now tell me, this are waiting, sir? Hello? Hello? Hello, sir? Sir, Sami, sir? Hello, sir? Are you there, sir? Hello, sir?
Yes, Prasad, yes.
Sir, you can continue, sir. Sorry.
ఓకే ప్రసాద్ ఓకే అదే నేను నాగేష్ సార్తో ఫోన్ మాట్లాడుతున్నాను మీ మాటలు ఇటు
Okay, sir.
ఓకే థ్యాంక్ యూ ప్రసాద్
Okay, sir.